Welcome to Saturday's edition of Cracking the Cryptic, where today we've got a puzzle by Udukos for you. Udukos is an absolutely world-class setter, so this should be a lot of fun, and it's got a very, very strange rule set. It's called Juosan Killer Sudoku, and I think Duosan is a logic problem invented by Niccoli in Japan. And I don't know that I've ever done a Duosan puzzle in my life, but I've read the rules of this one, and it seems to be something to do with parity. That's all I can say. Well, I love parity puzzles anyway, so this should be brilliant. Udukos is always brilliant, but I have to say the rules, the rules are going to take a little bit of explaining, but Udukos has been kind enough to provide an example here, so we'll be able to go through that and find out what's what. In other news, thank you so much if you joined us last night for our live stream of the return of the Obra Dinn. We made a little bit more progress before I got motion sick from going up and down the stairs, so it was a slightly shorter stream than usual. I did get motion sick once on the London Eye, which is quite phenomenal. If you've ever been on the London Eye, it does move very slowly in a circle. Nobody should really get motion sick on it, but it appears that I do. Theme parks and Simons do not mix. Anyway, we're going to be back. We'll be back to that probably Tuesday or Wednesday next week. So keep an eye on our Twitter for an announcement. In other news, the only other thing to mention is, of course, Patreon, where we have got a plethora of extra content at the moment, including November's monthly reward, which is this Sudoku hunt based around Japanese sum Sudoku. Japanese sum Sudoku is very fun because if you complete the puzzles correctly, you get a picture in the grid. It's sort of like a hybrid of nonograms and Sudoku, and I think 45 puzzles worth. So do have a look at that if you're a patron. I think we're heading up towards 6,000 patrons at the moment, which is just incredible. Thank you so much if you support us there. We do everything we can to make it worthwhile. And we have got some more treats in store for you in the coming weeks as well, I can tell you that. Anyway, with all that said and done, let's get on with Juosan Killer Sudoku. I'll read you the rules. We've got normal Sudoku rule supply. In cages, digits must sum to the small clue in the top left corner of the cage. Digits cannot repeat within a cage. So we've got normal Killer Sudoku rules. So let's take a quick look at that 18 cage there. The cells in it have to sum to 18, but what you can't do is something like that. Because although these digits do add to 18, and although these fives don't see each other by Sudoku, they don't share a row, column or box, they are in the same cage, so that's not allowed. So don't do that or you'll get the puzzle wrong. Now comes for the strange bit of the rules. Here we go. Odd digits, and Udukos is kind enough to remind us what the odd digits are, 1, 3, 5, 7 and 9, can appear consecutively for more than 2 cells vertically, but not more than 2 cells horizontally. Even digits 2, 4, 6, 8 can appear consecutively for more than 2 cells horizontally, but not more than 2 cells vertically. So let's deal with those in order. So odd digits, I think, can go we can have as many odd digits vertically as we want. But if we identified this pair of digits here as both odd, I'll use, what am I meant to use? Orange for odd, because they both begin with O. So imagine those 2 digits were odd. Well then, both of those 2 cells would have to be even, because if we had a third odd in a row, that's illegal. Now, evens work the other way round, so they're constrained in columns, so we can have as many evens as we like in the rows, but once we get a pair of evens in the columns, we then have to make sure that they are framed by odds to avoid a situation where you have 3 connected evens going vertically. What an interesting rule. Anyway, and that's the end of the rules. Oh no, I've got the example. Let's have a quick look at the example, see if we can understand how this works. So a quick look at the grid, I can see that each of the cages is adding up to the indicated number. I can also see that horizontally, red digits, which seem to be even, there can be a string of like 3 red digits here, 3 red digits here. But look vertically instead of horizontally, there's always just either singles or dominoes. Never does it extend beyond that. So if we look at the green digits now, which are the odd digits, you can see we can have 3 odd digits vertically. But again, horizontally, there is a problem in the sense, well, not a problem, but horizontally, you only ever get 2 odd digits maximum connected in a line, never 3. So that's what we're going to have to do in the puzzle. Do have a go. The way to play is to click the link under the video. Now I get to play. Let's get cracking. Now, okay, well, a quick scan of the grid here is not is not fruitful. All of these cages, I think, have more than one option. Only, I think the 14 cages have 2 options, so they're sort of binary. Everything else has at least 3 options, which is a worry indeed. Can we do something with these then? 14 is either 5, 9 or 6, 8. There's probably something we can do with that, and the reason I think that is that obviously 5 and 9 are both odd, 6 and 8 are both even. So if they were both odd, they would be horizontal odds, and then you'd have to frame them with evens. Aha! And that breaks the puzzle. Good grief! Right? Yes. So this is the start. This cannot be a 5-9 pair, and that is because by making this a 5-9 pair, you make this a 6-8 pair. That's both even digits. Well, not both, but they're both even digits. But now, because of the funny Juosan rule, both of those squares would have to be even in order to stop there being a run of 3 odds in the row. But now, those 3 cells are definitely odd, and they are 3 connected odd cells in the row. So I think this is going to be useful. So now we know this is not 5-9. That's got to be 6. Whoopsie. That's got to be 6-8. This has got to be 5-9. We can colour them in. Oranges, blues. The oranges mustn't be 3 oranges, so we go blue again there. Of course, when we don't have the same restriction on horizontal even digits. So what do we do now? And this is probably going to be where my lack of Duosan knowledge is going to come rather starkly to the fore. That square's got to be a 2 or a 4 by Sudoku. Go away, cough. Well, okay. Yeah, it's similar logic again, isn't it? We can't, they cannot be 3 odd digits in those cells, because that's going to break the rules. So there must be at least 1 even digit in that string of 3 cells, and that will be the 4th even digit in row 5. So that square has got to be odd. And that's in an 11 cage, so if that's odd, they're either both even or both odd, because this domino must add to an even digit if this is odd. So if they, yeah, it's the same sort of logic again, isn't it? If these were both even, now those 3 squares, we've done all 4 even digits in box 4, so these 3 squares would be odd, and that breaks the puzzle again. You've got 3 horizontal odd digits. So those 2 squares, which must have the same parity, because once this is odd, we know these 2 squares are even, so they're either both even or both odd, have now been proved to be odd. Oh no, that's even. I was going to say, I must get something one way round here, because I've got a domino vertically and a domino horizontally, and these are odd, so it's the horizontal version that needs to be capped out with an even, and that's going to be a 2 or a 4. And now I've got, yes, okay, now I've got 2 vertical digits, which are even, so they must be surrounded by odds. Oh, I like this so far. This is quite fun. So now this domino, yeah, okay, this domino is 1 of each. Should we have a colour for that? Yeah, let's have a colour for that. We'll have green. Green means a domino is 1 odd and 1 even, but we don't know the order. Okay, so now what do we do next? 14, I don't think we know anything. 8. Oh, I see. Yes, lovely. In fact, that's really clever. Okay, so look at this 8 domino here. Again, it's an even number in 2 cells, so it's either double odd or it's double even. Well, it can't be double odd because that's going to make 3 odds in the row. So it must be double even, and that means it's a 2-6 pair. It can't be 1-7 or 3-5. Oh no, I was about to put that one in as odd, but that would be nonsense. Oh, 10 cage. 10 cage now can't contain an even number because it can't be 2-8 or 4-6, so that's odd. That's horizontal oddingness, so that must be even. That must be even. We've got to avoid vertical evenness, so that's got to be oddness. This is just lovely. Now this square has to be odd, because if that's even, those 3 are odd, and that's 3 horizontal odds again. So that's got to be odd. This has got to be a domino. Now, do we know something we didn't know before about the 18 cage? We know that the 18 cage... Yeah, right, this is such clever, clean, elegant setting. This has now become odd. So let's think about how we make 18 in 4 digits if one of them is odd. Well, one option actually would be for all 4 digits to be odd. They would sum to an even number, and we could make them sum to 18 if we missed out the 7. But that would make those 3 squares odd, which is impossible because of the Juosan rules. So this cannot be 4 odd digits, and therefore it must be exactly 2 odd digits and 2 even digits to make sure the parity works, because we're adding to an even number. And this, right, so there are 2 even digits in these 3 squares, but they cannot be vertical because that will create an evenness problem vertically. So there must be an even in this square to avoid that, and that's, well, that's a vertical green domino. Do I want to highlight that or not? The answer to that is I am not sure. I don't know. Maybe is the answer. Let me just have a think about this. Can we learn more about the world here? The 27 now. Do we know what that's made up of? There are 2 evens in the box. So this, yeah, and this is an odd number. So it needs an odd number of odd digits in its sum. Now, it can't have 1 odd number in its sum, because then there would be 3 evens in the box, which is nonsense. So it must have 3 odd numbers in its sum. Right, so let's max out the odds. 9, 7 and 5 would be 21, and a 6 would go along with that. So that's, hang on, is there any other way of doing that? What about 9, 7? Yeah, 9, 7, 3 and 8 would also work. Okay, so we know there's 1 even in there. 1 even and 3 odds. And we know it's got 9 and 7 in it. Do we know that? Yes, we do. It must have 9 and 7 in here. But we don't quite know how the other 11 is made. It's 3, 8 or 5, 6. Do we know anything there? No. Okay, sorry. I'm not quite sure how to do that. There's probably some Duosan rule that tells us the answer. Right, we're going to have to think more. Okay, so let's have a look at row 3 maybe. We've got 3 evens. If that was even, this would be double odd, and that would be even. That would work regarding parity, wouldn't it? Okay, alright, now I'm stuck. I will accept it. That square's got to be a 4 or an 8. Maybe it's Sudoku that's going to help us. 14. The 14 can't be all even digits now. Because if it was, these would both be even, and that would break the puzzle. So there must be an odd digit in here, which means there must be 2 odd digits in the 14. So the 14 is now exactly equal to 2. Oh, I see. Right. I said that could be 2 odd digits. No, of course it can't because of the Juosan rule. So that if that can't be 2 odd digits and it can't be 2 even digits, that is a green domino. And that's one of each, which has odd parity, so that's an odd digit. This is mad. That's now even to avoid a string of odds going horizontal. So that's even. 7 is odd. These are the things we get to tell you on Cracking the Cryptic. 7 is odd, so it must have an odd number in it. Good grief! And now if you look at row 3. We've got an even. We've got the 4 evens accounted for: 1, 2, 3, and 1 in the green. So those 2 squares are odd. That square now is even, isn't it? Because didn't I say there was exactly 1 even digit in here? I did. So that's got to be the third. Well, 3 plus 1 is 4 even digits altogether. 1, 2, 3. Okay. Right. Right, okay, here's a simple-ish deduction. That can't be a 2 anymore, because if that was a 2, that's putting a 2 in a 27 cage, where it definitely can't go, because the other 3 digits could never add up to 25. So that's a 4. Oh, and if that's odd, that's even, of course, isn't it? We knew that was a vertical green domino, I just forgot. So what does that mean? So that means this square, which is in the 18 cage, is either 2, 6 or 8. There's a 4 or an 8 in the 14 cage. Oh, that's rather clever. Right, okay, let's think about this 27 cage again. If that has a 4 in it, which it could have, but if it has a 4 in it, the other 3 digits are going to be 6, 8 and 9, and that square's not going to have a fill. So there is no 4 in the 27 cage. So where does the 4 go in box 3? Exactly there. So now there's an 8 in my 14 cage with 2 odd digits which add to 6, which must be 1 and 5. Oh, good grief. That's not 8. The 7 cage now doesn't have 1, 6 or 2, 5 in it. So this is 3, 4, and we know the disposition of the even and the odd digit. 4 by Sudoku goes here. It's very clever as well, isn't it? The way it's sort of mixing up the Duosan rules with the Sudoku rules. Oh, that 10 cage now can't be 3, 7, so that's 1, 9. So there's no 9 in those cells. Have we worked out yet whether this is 3, 8 or 5, 6 as its extra digits? No, we haven't, have we? We know that there must be a 2 vertically in one of those squares. So this square is never a 2. So now this 18 cage is either this domino is adding up to 8, which could be 1, 7 or 3, 5. Or if that's adding up to 12, this is adding up to 6 and must be that's not 8. Because if that's 8, this domino has to add up to 6 and has to be 1, 5 because it's odd digits, and that's going to make both of those cells have to equal 8. So that square is a 6. Now 6 is pushed into the 27, and now we know that's got to be 6, 7, 9 and 5 adding up to the correct total. Which means this is a 2, 8 pair, I think, in the column. Oh, I've just noticed as well, this column's got 4 even digits in it, so all of those have got to be odd. Those squares, these 2 squares add up to... Oh. Yeah, well these add up to 8, but I'm just noticing that in this box, those 2 squares have to be a 1, 3 pair. So this is either a 5 or a 7. And I see how this is going to unwind. Look, we've got a 1, 3 pair here, so that's making that a 5, 8 pair, which means this square is a 1. This 5, 8 pair. Oh, I thought that was going to unwind this one. It doesn't. Oh no! Oh, you rotten thing. No, it doesn't. That square's a 7 or a 9. Sorry. Oh, good grief. Okay. So now we're going to have to... 9 is not in those cells. Oh, we've got 1 9 here, so that's 7. Right, yeah, okay, so we've got to do more Sudoku. And if that's 7, this cage has to be 1 and 3. So there we go. We have figured this cage out, finally. Those 3 squares have got to be 3, 5, and 8 in some order. There's probably some Juosan trick we can do. We can't have... No, we can have vertical odd digits, just not vertical even digits. 5. Oh, we can remove 5 from those squares. These squares have got to be the odd digits that aren't 1. So that square is quite restricted. That's become 3 or 7. An 11 cage in 3 cells that are all odd. I can do that. Oh, you... I almost swore at myself then. Right, how do you make 11 in 3 odd digits? 1, 3 and 7 is the only way that will work. That's not a 1. So there's a 1 down here in one of these 3 cells. This square is a naked single. It sees 9, it sees 1, 3, 7, so that's got to be 5 given it's odd. And those 2 squares now, oh, we don't know because we don't know what this digit is. Oh yes, we do, we've got that digit. Oh, good grief. Right, okay, so that's 2. This square is a 4, 9 pair. These squares are a 2, 6, 7 triple. Can we do any better than that? We can... maybe, maybe not actually. 9, 3, 5, 8. Oh, if that's 3, 5, 8, that's resolved. That's 2, that's 8. So that's not 2. 2, 6, 7, 5, 6, 7, 6, 7. Oh, we can't work out. We still haven't done this box at all. It's got 3 odd digits in it and 1 even digit. So I can't tell how we're going to resolve this. That's... oh no, you can have vertical odds, so stop looking at that, Simon. You can have horizontal evens, so that's fine. Oh dear, what are we missing here then? 2 has to go in that domino, so there's a 2 in one of 3 places in the middle box. 4 is in one of 3 places in the middle box. One of 2 places in the middle box. 5 is in one of 3 places in the middle box. Okay. No, I can have vertical odd digits. Ah! Where do we look now? Is it something to do with the 26 cage? It's quite interesting there are odd digits down its... Ah. Yeah, okay. Well, I can tell you that there've got to be 3 even digits in the 26 cage, because if there weren't 3 even digits at least in this 26 cage, then one of these dominoes, either this one, or this one, would only contain odd digits, and that's not going to work, because if any of these dominoes are just odd, they're going to pair up with their friends on their right and make 3 odd digits in a line, which is illegal. So there's 3 evens. This is very clever. There are 3 evens at least in the 26. Well, how could there be only 3 evens? If there were 3 evens, the other 3 cells would be odd, but the parity of the box would then be odd, and 26 is not odd. So there must be another even. There must be all the evens, which add up to 20. 2, 4, 6, and 8. And a pair of odd digits, adding up to 6, which are 1 and 5. So we actually know this box. This box is 1, 5, and all the even digits, which is a slightly well pencil marked box. Ah, yeah, but hang on, we've got 2, 4 and 5 in box 5 up there already, so those squares are not 2, 4 and 5. 1, 6, 8 here. 2, 4, 5 down here. Is that putting pressure on the 21? 2, 4, 5. Ah, yeah, it is. Ah, the selection. The selection of 21 for this cage is brilliant. It is brilliant setting, because now, well, this is too beautiful not to be deliberate. Is there a 9 in the 21 cage? No, because if you do put a 9 in there, the other 2 cells in the 21 cage have to add up to 12, which means they're either 3, 9, well, they're not that, because that would put 2 9s in the box, 4, 8, they're not that, there's a 4 in there, or 5, 7, they're not that, there's a 5 in there. So there's no 9 in the 21 cage, and if there's no 9 in a 21 cage, it must be 6, 7 and 8. And that means those are not 6s and 8s. Oh, I see. So now we get a 6, 8 pair here, and 6s and 8s are both even, but they're horizontal even, and that's allowed. 6, 7 and 8. Okay, so there's 2 evens and 1 odd in there. And 1, 2, 4, 5. Oh, right, okay, so these are both odd. Oh, in fact, we know they're 3 and 9. And they are indeed both odd. Now we've got 2 odds here. So that must be even, which is almost clever. Oh, no, it is. No, that's good. I'm going to come back to this. That's even as well, though. I just want to record that. And that's got to be 2, 6 or 8. But look, now I've got a 6, 8 pair in this column. So that square's got to be 2. And that square's got to be 6. Ah, and then we play boomerangs, because that 6 is now bouncing back down there, making this square a 6, making this square a 6, making this square an 8. Which means that square is not an 8, and this square is an 8. And 8 is even. That, therefore, is odd. Wow. Okay. 2 is not there anymore, look, because of this 2 here. 7, 8 here. Oh, I see. Okay, so 2 has to appear in this 1, 2, 4, 5, 2 by 2. So it's not there. So it's definitely here, which means it's not there. So we get 2 in the middle box, and we blew it out. I was about to say you can't have 3 in a row, but of course you can, because they are even. Ah, but what you can't do is have 3 evens in a column, so that's odd. Do we know what that is? The answer is I don't know. Oh, in fact, actually I've got a full count of evens now. That one, that one, that one, and there's an 8 here. So that must be odd. Which means that must be even, to avoid the oddity problem. Now that's therefore a 4, therefore this square is a 9, and of course is odd. We can have vertical odds. We can't have too many vertical evens, so that square is odd. We can't have 3 odds in a row, so that square's got to now be even, which means it's not 1. This is just brilliant, isn't it? Now this square is a 6 or an 8, and we've done all the evens for this column, so they become odd. And in fact, oh, we know what they are. They're a 1, 7 pair, look, because we've done 3, 5 and 9 in the column. We've done all of the evens in row 5, so they are odd. Wow, okay. Now, what else do we know? We know that there's definitely... Oh, right, okay. Here's something I hadn't noticed. There's definitely a 2 in this domino. So there can't also be another even digit, or that's going to be 3 even digits in this column. So the 4 must be there, I think. So there's a 2 here, there must be a 4 here. Oopsie, I mean there must be a 4 here, there's no 4 there. So that means that that square is not a 4. Whoopsie. Well, it means this square is a 4. We'll tidy up this one in a second. That therefore gains its even status, completing the evens for this column. This square is now odd because we've got all of the evens in the box. That square is a green domino because it's got an 8 in it and some other digit that's odd. And I'm sure this is very, very, very clear what this all means. Although I can't quite see how to do it. Let me just stare at this for a moment. Is this a green domino as well? Yes, it is. Another green domino. This time with a 2 in it and an odd digit. So 2 is in one of these squares. 4 is in one of these squares. Can we do any better than that? That's the next question that we're going to grapple with. 5, 9 here, so there's got to be a 5 and a 9 in those squares. This has got to be from 1, 3 and 7. This square is not 7. Ah, right, okay, I think we're back to Sudoku now. There's a 1, 3, 9 triple in column 6, so that square's not a 1. So that means we've now got a 2, 5 pair here and a 1, 4 pair here. Hang on, let me just get rid of the 5. 1, 4 pair means that square's not a 1. Oh, in fact, look, a 1, 4 pair means that square is a 9. This square is a 1. That square is a 3. That's a 7. That's a 1. That's a 9. That's a 3. That's a 3. That's a 5. That's a 5. I don't believe it. Now we've got a 1. Yes, we have. We've got a 1, 9 pair. 9 goes here. 1 goes here. Oh, I see. So these are from 2, 3 and 7. And these ones are from 1 and 8. Now we must be able to do some tidying up, I would think, as a result of this. What have we learnt in terms of the whole Juosan analysis? We have learnt that we've got to avoid having 3 evens in a column here. So if that's a 4... Oh yes, actually, we've got to also avoid having 3 odds in a row. So this is all very, very constrained. Because we've got to avoid 3 odds in a row, one of these squares is even, one of these squares is even, but we know we can't stack the evens in a vertical column because then we're going to have 3 evens vertically. Nori nori. So that means that the evens are in a sort of checkerboard in this 2x2. They're either like that or like that. So if that's a 4, that will be a 1. I don't know what that means. Well, okay, you know, if that's a 4 and that's a 1, that's a 2 and that's a 5. So the 4 and the 5, there's always a 4, 5 pair and a 1, 2 pair here. 4, 5, 1, 2. Is that putting pressure on the 9? The 9 is the only clue I've not used yet. Let's have a think about this box then, I think. We've got to put 4 in one of those cells. Can 4 go here? The answer is no. Actually, it can't. If 4's in the 9 cage, that's a 5. And now you can't put a 5 in this column. So 4 is not there. 7 can't go in the 9 cage because look, we've got a 2x2 of 7s here. How many 7s are we expecting in the bottom 2 rows of the grid? The answer is 2. By the rules of Sudoku, there is only 1 7 in this row, there is only 1 7 in this row. So if I was to put a 7 in the 9 cage, that would be a third 7 in 2 rows of the grid. That won't work. So there must be, in fact, there must be a 7 in one of those 3 squares. No 7s there, no 7s here. So this is not 4, 5. It's not 2, 7. So it's either 1, 8, which creates a deadly pattern. I won't use uniqueness to say this is impossible. In fact, in Duosan, maybe you can break deadly patterns using the pattern of the parity. I'm not sure about that. It's either 1, 8 or 3, 6. Look, so there's 3, 6 would have to go that way round. And just to explain what we'd be worried about if this was a 1, 8 pair only, is that there would be nothing in the... If we ignore the colouring for a moment, there would then be nothing in the puzzle's internal logic that would distinguish this solution from this solution. So the puzzle would have 2 solutions just by switching the 1s and 8s around, and nothing in the puzzle's own internal logic would differentiate those. A puzzle with 2 solutions will never appear on Cracking the Cryptic unless something has gone very badly wrong. So this, knowing the puzzle has a unique solution, we could actually write 3 and 6 in here. Now what I'm not clear about is whether the Juosan rule allows that logic to function in a puzzle like this. I'm certainly not going to rely on it anyway, so I don't even know why I mentioned all that, but I did. So how do we differentiate whether this is 1, 8 or 3, 6? If that was an 8, that would be 3, 6. 7, 8, 7, 7. Oh no, this is right, that's beautiful. Right, I understand. In fact, this is 3, 6 because it doesn't matter how this works. Right, if this is a 1, then obviously this is a 3, 6. If this is a 7, then this is an 8, and that's still 3, 6 there. That's beautiful. That is absolutely beautiful. So this little domino here tells us that this is a 3, 6 pair, and that must go that way round. We know the parities, and that parity is helpful. In fact, this is more helpful than even the parity, because now 3 must go here in column 7. We've got a 5, 9 pair here, so this must be 7. We've got no 3s in there, so this has become 2, 7, but that might not be as important as the fact that this, we can't have a third odd in this cell. So that's forced to be even, therefore the checkerboard forces that to be even, that to be 1, 5. Fill those in blue, fill these in orange. Can't have a third orange in that line, so this is going to be even. That's not a 6 look anymore because of this 6. That's 2 or 8. This 1 is giving us a 1, a 7, a 7 and an 8. We can do the parities. Let's do the parities. 4 in the row has to go there. Fill in its parity. Fill in this one's parity. We've got, we've got 2 odds vertically, which is fine, and we can have another one as well. Oh, but we can't have another one horizontally, so that's got to be even. So this is now a 2 or an 8, which... Oh, I see. So now we've got a 2, 8. We need to put a 4 in this row. So that's got to go there, which means that's even. This is now odd, not 4. In fact, it's a 1 by Sudoku. So that's a 1. That's a 1. That's an 8. We now know the parities. Douche, douche. Okay. Have we learnt any more parity magic from that? 6 can't go in those cells, so this is a 7, 9. Can we do better than that? 3, 1. Oh no, there must be something we can do here. 6, 7. There's definitely a 9 in those cells. Can't see. I'm sure there's something we can do here. What about this square? That square has to be a 5 or a 9 by Sudoku. This square has to be a 2 or an 8 by Sudoku. Oh, so that's fixing these two at least. So we get a 2 here, a 7 here, and we can sort those parities out. 7 comes out of those 2 squares now. That still doesn't seem to be resolved, which is very odd. Can we do a Juosan trick? We've got 3 odds to put in there. No, we can't. That's not going to help us. It needs to be Sudoku. Sudoku has to figure these out for us. So something needs to go on over there, I think. Right, this 9. Let's carry on with Sudoku then. 9 and 5. 5 goes here. 5 goes here. 8 goes here. 8 goes here. 6 goes here. 6 here now. This 8 means that's a 2, that's a 2, that's an 8. We need to put an 8 into this box, which must go there, finishing off the parity for this whole bottom left-hand corner. This has got to be 9. That's got to be 3. That's 3. That's 7. Right, that's 6. That's 2. And that's 7. And that's right. Finally, look. It looks like we've managed to find our way into the top right-hand corner. Well, we're not going to be able to put a 3, but we did put a 3 in the corner there. And that means that's 3 in the corner. That's 3 in the spotlight, losing its religion. That's going to be, they're both even. Let's put those in. That's definitely odd. This is now a 5, that's a 6, that's a 9, that's a 7. And we can odd all of those. Even that one. Fill in the 9 and the 5. Don't miss out the 9 and the 5. And click here, and that's how to solve the puzzle. Absolutely brilliant. That was so much fun. It's, well, it's udukos. It's classic udukos. There's about, I don't know, 30 different beautiful logical steps in that puzzle. Probably that's not an underestimate. Somebody might be able to count them. I'd love to know how many. How many non-trivial deductions did udukos build into that puzzle? Because it felt like constant. There was constant from the start with the disambiguation of the 14s, and then it sort of, we made our way, didn't we? We managed to figure out that was an odd triomino. We got some Duosan logic here, which gave us, we got the 8 in very nicely. This digit was very nice, and the logic interacting this 18 with this 14 cage was very nice. We managed to figure out the 27 cage. It was just constantly flowing gorgeousness. And then very clever down here, this run of odd digits, actually forcing the exact composition of the 26 cage. And then that, in turn, and the fact there had to be some digits in here, forcing the composition of the 21 cage. Even the selection of this 9 cage here, and the fact that it was resolved either way by this domino. It's just fascinating and supremely clever. Udukos, take a bow. Thanks so much for watching as well, and we'll be back later with another edition of Cracking the Cryptic.